Hi, this podcast is all about equilibrium constants versus the equilibrium quotient, which is Q. So the equilibrium quotient I like to find in value or think of in terms of a question. I'm questioning where I'm at in relationship to my equilibrium constant. And this is always given. Always. Okay? So if I know the value of my equilibrium constant, okay, and I want to find out where I'm at in a certain reaction, I'm going to go ahead and ask a question. And so that's what Q is. It's a question. A reaction quotient becomes a question in my mind. And that reaction quotient can be in three places. It can be equal to my equilibrium constant. It can be less than my equilibrium constant, or it can be greater than my equilibrium constant. Let's go back and look at this for a second. So if I know my equilibrium constant, let's just say my equilibrium constant has a value of 5. Okay? And I do an experiment and I put things in just like I would at equilibrium. I have a certain reaction, right? For instance, I have this reaction. And I put all my components in and, all of a sudden I find the equilibrium constant. But you know what? I measure it and it actually measures something like, 7.2. I go, wow, that's greater than 5, isn't it? So guess what? I'm not at equilibrium. How do I know I'm not at equilibrium? Because my value from my solution from my math problem is not at 5. What do I have? I have a value that's greater than 5. And so where am I at in terms of equilibrium? Well, I've got more than I need. As a matter of fact, I've got more products right now, because this is what happens in my equation, right? In this, like my arrow, these are my reactants, these are like my products. I've got way more products, and so they need to break down. I need to have my reaction shift to the left to reach my value of 5. My value of 7.2 is greater than 5 right now, so my Q is greater than K. So my my products need to shift. I need to shift to the left to reach equilibrium. So let's go back to a different scenario. What if I put everything into a container, into a nice little beaker like normal, and I come up, remember our value is 5, it always is going to remain 5. Okay, what if I come up with a value of 5? I say, oh, guess what? Where am I right now in my reaction? Well, my question is equal to my value of K. So I must be at equilibrium. How about that? So this is what happens when K is equal to Q. And we'll find all this out in a second, okay? So if this confuses you, just skip this slide and go to the next one. Right? Now, what about my next scenario? Well, let's say I put a bunch of stuff in a container and I react it, and all of a sudden I come up with something that's like 3. Well, what's true? Well, I'm going to call this Q, okay? Because it's not my equilibrium constant. I'm questioning things. I'm wondering, if I put a little bit of this and a little bit of that into my reaction, what's going to happen? Well, what's true with our value? It's less than Q, isn't it? And so what's true? If I have less than I normally have, that means I have way more reactants than I should right now. My reaction needs to shift in this direction to equal my value of my equilibrium constant. Okay? So let's try a problem, and maybe this will make more sense. Just remember this little line. Now, you know that you're doing this kind of problem. And by the way, this has 3 parts, A, B, and C. Okay? Now, in A, which system is the equilibrium? So that means A, B, or C. Is A in equilibrium? Is B in equilibrium? And C in equilibrium? If not, which way does it need to shift? So the very first thing you need to know when you have this kind of problem is this, which way does it need to shift? That tells you you're doing a Q problem. Okay? They always give you K, so here's your value for K. And so you're going to ask yourself, what do I have in an answer to my problem? Is it equal to 2.4 times 10 to the third? Is it less than 2.4 times 10 to the third? Is it more than 2.4 times 10 to the third? So the very first thing you always do is you always write an equilibrium expression. So I'm going to go ahead and write N2 times O2 over NO, and I'm going to go ahead and put that to the second power. Now, normally I would be right, that's equal to K. I don't know where I'm at, so I'm going to question myself. So I write Q, and my clue to that is, if not, which way does it need to shift? I'm not sure where I'm at. Now, what goes in these brackets? Well, what goes in the brackets is molarity. So how do you do that? Well, to find molarity, don't you need to do moles over liters? Okay? So what's true here? For NO, I have 0.024 moles per 1 liter, right? Using these values right here. And so I know for a fact that I'm going to go ahead and I'm going to have 0.024 down here. And my directions say to square it. Correct? Now, what do I do for N2? I have 2 moles of N2 over 1 liter, and I have 2.6 moles of O2 over 1 liter. Right? This is for nitrogen, and this is for oxygen. So guess what I'm going to put in for those values? I'm going to put in 2 moles here, and 2.6 moles here. Moles per liter. Moles per liter. Moles per liter. That's molarity. Now, I'm going to go ahead and do my math. And when I end up doing my math, I end up with 9.0 times 10 to the third. That's my value for Q. For these amounts of reactants and products, when I put them into this equation, this is what I end up getting. So I want to ask myself, where am I in relation to K? Where am I in relationship to 2.4 times 10 to the third? That's my equilibrium constant. Where am I? Well, 9 times 10 to the third is a bigger number, isn't it? Aren't I over here? So what do you have? You have a number that's way bigger, okay, than your equilibrium constant. So there's actually like a number line or a letter line, and this was K and this was Q. Which way would it have to shift? To the left. It needs to shift to the left. And what do you have in terms of your products and reactants? Well, these are your reactants and these are your products, aren't they? So where are you? You have way more products right now because you're way over here on this line. You need to shift back to this direction, to the left, to reach your equilibrium constant so that you're at equilibrium. Let's try another one. Which system's at equilibrium? Let's see if this one's at equilibrium. Well, look at this. Our K hasn't changed. This is still the same reaction. It's still the same temperature. It still has the same value for the equilibrium constant, right? See that? 2.4 times 10 to the third. But now we've got a different amount of stuff. Look at the different stuff we have now. Now we have a 2-liter flask. And I'm putting a different number of moles in, right? These moles are not the same. I erased them, sorry, but they're right here. See? These moles are not the same. Molarity is not the same. But the conditions where it reacts is at the same. So I'm going to go ahead and put these values in. And when I do my math for, and by the way, let me label these so it's clear to you. This is for NO. And this is for N2. This is for O2. So what are my values for that? For N2, it's 0.31. So I put 0.31 right here and follow my directions. Okay. For O2, I go ahead and I get 2 molar. And for NO, which I'm going to square, why am I squaring it? Because that's what my directions tell me to do. My value is 0.016. And when I do my math, I come up with 2.4 times 10 to the third. So what's true? Hey, look, my Q, my question, is equal to my equilibrium constant. And so therefore, what's true on that equilibrium letter line? I'm equal. I must be at equilibrium. And so I was answering right now, which system's at equilibrium? Well, B is. And does it need to shift? No. Why? Because it's at equilibrium. How do you know? Because your numbers match each other. Let's try C. Now, this is how you write your equilibrium expression, which we can call K, but in this case we're going to call Q, because we've got these certain molarities, and we're going to go ahead and plug them in and see where we're at. So if we plug these into the right spots, okay, I'm going to go ahead and put 0.8 molar here for nitrogen, and 0.57 molar here for oxygen, and 0.02 molar here, and square it. Why am I squaring it? Because that's what my directions tell me to do. And when I do that, I come up with a value of 1.1 times 10 to the third. Well, where is that in relationship to K? In relationship to our equilibrium constant, if we were to draw a little letter line, here's my value for K. What's my value for K? 2.4 times 10 to the third. What's my value for Q? Well, my value for Q lands right here, isn't it? 1.1 times 10 to the third. It's smaller than my value for K. So that tells me, what do I have? What lives on that side of my reaction? I have way more reactants. And my reactants are not done reacting yet. They need to shift to the right until the value of K is reached. And so is this at equilibrium? No, it is not. So the reaction needs to shift to the right to reach equilibrium.